So let's continue the class. I think we stopped somewhere here, right? Here. Yes, we stopped there. Features that decreases the predicted stability. You guys can read that. It's in English. So when you draw your resonance structure, and when you draw the resonance structure and you want to determine which of those resonance structure is a greater contributing structure towards the overall hybrid, those are the things that you want to look at. And we've talked about that already. Do all the atoms have complete octet? If there is one that doesn't have a complete octet, chances are that it will not be the best resonance contributor. Then look at the negative charge. Like I said, you want the negative charge to be on the electronegative atom. And then if a positive charge is on an electronegative atom, that is not good news. Okay? And you want the charges to be as far from each other as possible. Then with delocalization energy, the more delocalization, the greater the stability. And electron delocalization is another name for saying resonance. The more resonance, the greater the stability. Okay? That's just it. Blah, blah, blah. This is the same story like what we've been saying. The greater the number of relative stable resonance contributors, the greater the delocalization energy. So, depending, in this case we have two examples. If you look at this molecule and you look at its resonance structure, they all have two resonance structures, but you notice that this resonance structure is relatively unstable because we have a positive charge on oxygen. That's what makes that resonance structure relatively unstable, compared to this one, where they have almost the same stability. Okay, those ones have almost the same stability. Now, what I want us to look at, well, it's the same thing. I will skip this one, the greater the resonance structure whatsoever. What I want us to look at will be isolated and conjugated diene. That's where I want us to start from today. So, if we start by looking at the name, diene, we have the ENE, that stands for the double bond, and the di means two. So, dienes are molecules with at least two double bonds. Okay, with two double bonds, to be precise. Those are diene. And there are different ways in which you can arrange those double bonds. You can arrange those double bonds in successions, or in alternation. One double, one single, one double, one single. And so when the double bonds are arranged in that kind of alternative way, we refer to them as conjugated diene. Okay? And what you need to notice in conjugated diene is that all the carbon atoms will have the same hybridization. They are all sp2, sp2, sp2. Do you see that? All those carbon atoms are sp2. They are the atoms involved in the conjugation. Now, sometimes the double bonds might be separated by an sp3 carbon, by one or more sp3 carbon. Those kind of systems are referred to as isolated system. In this case, you will notice that this guy here is sp3 hybridized, whereas these other ones are all sp2 hybridized. Does that make sense? So isolated system are separated by at least one sp3 carbon, whereas conjugated systems have no separation. Now, between isolated system and conjugated system, which one is more stable? Then I can skip the next slide. You guys know the answer. So to determine that stability, one thing we can do is the hydrogenation, heat of hydrogenation. We've done that in the lab. And so when they did that in the lab, the lower the heat, the absolute, heat of hydrogenation, the absolute value. Okay, heat of hydrogenation. The smaller that value is, the more stable the system is. And so when you compare 1,4-pentadiene, which is an isolated system, to 1,3-pentadiene, which is a conjugated system, we notice that the 1,3 will have a smaller energy, in this case 54, compared to the 1,4, which has a relative greater amount of energy. Then the guy with the smaller energy is the more stable. So, conjugated dienes are more stable than isolated diene in terms of heat of hydrogenation. Does that make sense? In terms of that heat of hydrogenation. And if they are more stable, one thing they can also do is to resonate. They can form resonance. Just remember, the more resonance, the more stable the molecule is. And so with conjugated diene, for example, the one we have over here, we can have the resonance structure as shown here. Let's follow the red arrows. Let's focus on the red arrows. So first thing you need to take note is that all the atoms here are sp2. Do you see that? They are all sp2. If they are all sp2, it means that they have at least one p orbital. So those p orbital electrons can jump from one orbital to the other. That's what actually causes resonance. So the electrons here move to this and create this double bond. By doing that, this particular carbon becomes deficient. That's why the carbon is having a positive charge. Okay, because it becomes deficient. Now, the electrons on this bond at the same time move now and goes on top of the carbon atom. That's why we have that negative charge on top of carbon. So that's our resonance structure. Okay, the same resonance structure can be obtained, or similar resonance structure can be obtained if you follow the blue arrows. You obtain a similar resonance structure. From there now, you can have your hybrid structure that cut across all the 4 atoms that are involved in that diene system. Does that make sense? Although you have these 2 resonance structures, what you guys need to also notice is that this particular structure here is more stable. That particular structure is more stable compared to this one. And the reason is clear, right? This carbon atom here does not satisfy the octet. Those are the reason. That carbon atom doesn't satisfy the octet. Now, structural properties of isolated versus conjugated diene. In terms of structure, we notice that in conjugated diene, just like we said before, all the carbons are sp2. All those carbons are sp2. It means that the sigma bonds that are formed in conjugated dienes, we refer to them as sp2 bonds. Those are sp2 bonds. But if you look in isolated diene, this is sp2 and this is sp3. So there exists an sp2 bond. Does that make sense? There's the existence of an sp2 bond. And remember, the shorter the bond is, the stronger the bond. And double bonds are usually shorter than single bond. So this sp2 bond will have a double bond-like character. It will behave more like a double bond. So it will be shorter compared to this guy, sp2 which is kind of like partial double bond, partial single bond. So that bond will be longer, okay, in terms of bond length. So in conjugated diene, the bonds are shorter and stronger. And if they are stronger, it is hard to break. Does that make sense? If a bond is shorter and stronger, then it's hard to break, meaning that it is stable. Does that make sense for everyone? Okay, that's the way I want us to think about it. And so you have a table here that summarizes those bonds here in terms of their hybridization. And so if you go down the table, you'll be tempted to say you're increasing in stability, because as you go down, those bond decreases. You have an sp-sp bond, which is stronger, shorter, and then you have, for example, an sp2sp bond, which is also shorter and stronger. Okay, so the shorter the bond, the stronger the bond, and chances are that the molecule becomes more stable. Question? Hey, the students from Dr. Nokogu's lab, we're meeting at 2 o'clock. We're meeting at 2 o'clock during my lab, or you meet me earlier, because I'll not be around at 6 o'clock. Sir, inform your friends. Huh? All of you guys have classes at 2? When will the class end? Yes, maybe let's meet then at 3:30. It will not be a long one. It will be a very short one. Okay? Yeah, thanks. Text your group, text them and tell them. It will be a short lab. Even my lab at 2 o'clock will be a short one. A very short one. So that we should not contract corona. Yes, let's avoid having that. No, that's not the reason. It's because it's a short lab, naturally. Karina, you're so happy, right? Okay, so there's a third type of system that we haven't talked about, third type of diene system, okay? Those are cumulated dienes, where you have double bonds that follow each other in succession. Remember, we've talked about conjugated diene, we've talked about isolated, but now you have cumulated dienes, where the double bond follow each other. So you have a double bond, then another double bond, okay? And with those ones, we notice that if you have to look at the carbon, this guy will be sp2, this guy will be sp2. What about this one? What is the hybridization of that middle carbon? What is the hybridization of the middle carbon? That middle carbon will be sp hybridized. Does that make sense? Now, if you look, then it means there will exist a certain type of bond. There will exist the sp2sp bond. Okay, how is that bond? Shorter or longer compared to an sp2sp2 bond? We expect that bond to be shorter, right? And so if we expect it to be shorter, what do you expect in terms of stability? We expect that that will be a little bit more stable. Ah, perfect. That's it. Now, application. This is just for your information. These conjugated dienes are very useful because the more conjugation you have, the more colorful the substance is. In chemistry, all the colors you see is because of conjugation. The blue color, the green color, or whatsoever, that's simply conjugation. The molecules that constitute those colors are conjugated. They're conjugated system. And in the industry, in the tech industry, they take advantage of that to build this LED display. So all the colors you see in those fancy LED display are just conjugated molecules that you have in there. So if you want to use your chemistry to get into the tech industry, that's probably what you will spend your whole life doing. Trying to build different types of conjugated systems that will generate different types of colors. Does that make sense? And that's what's mostly used in your phones and everything now. They are simply conjugated systems. Yeah. They are simply conjugated systems. That's just an application. Now, the allyl system. The allyl versus the benzyl system. This is more of a review because we already know what they are. The allyl system is made up of three atoms at least. Okay, and over here we have an example of what we refer to as the allyl cation. And when you look at the allyl cation, what I want you guys to have in mind is that this particular cation can easily undergo resonance because we have that XYZ subsystem in there. Does that make sense? That's our allyl cation. And so that's what makes the allyl cation stable, because it can undergo that resonance. Okay. Now, the benzyl cation technically is another form of the allyl cation. Okay, because if you look at the benzyl cation, you can also see the XYZ system. But this is simply benzyl because of the presence of that benzene ring. That's what we refer to as the benzyl cation. The presence of the benzene ring. So the benzyl cation is also stable. Now, between the benzyl and the allyl cation, which one do you think will be more stable? Chances are that the benzyl will be more stable. Okay? And the reason is simply because the benzyl can form more resonance structures, as we'll talk about in the following slide. We'll look at the different resonance structures that can be obtained from the benzyl cation. Does that make sense? Now, for allyl cations, in order to draw the resonance structure, there is a particular way the arrows move. So if you have your allyl system, XYZ plus, the way you have to draw your arrows to indicate the resonance is that the electrons will leave from XYZ. The electron will leave from XY and then form a new bond between Y and Z. And so your resonance structure will simply be this. And the positive charge will migrate to the X. So that's the general way of drawing resonance structure for an allyl system. And so that's also true for the benzyl system. Okay? Take note that this is a little bit different from the other system. This is a little bit different from when you have X equals Y minus Z with a lone pair. When you have X equals Y minus Z with a lone pair, the way you draw your arrows is a little bit different. In this case, the way you draw your arrow, you start from the lone pair and then create a bond between Y and Z. Then the electrons here move to X. And the resulting structure will be X with lone pair minus Y equals Z. Then because X has the lone pair, there will be a negative charge on X and a positive charge on Z. Yes? No. I just want to show the difference in moving arrow between the system. If you have an X equals Y minus Z with a lone pair, that's the way you move the electron, and that's how your resonance structure will be. Okay? If you have this kind of system, that's the way you move the electron, and that's how your resonance structure will be. In the case of the red system, Z will usually be an oxygen or a nitrogen. In that case, in the first case, Z will always be either an oxygen or a nitrogen. Does that make sense? We'll look at some of the examples. We'll probably see some of the examples. So, that said, that's how we can draw the resonance structure for the allyl cation, just like what we have here. This is my X, that's my Y, and that's my Z. Just like we said before, you move the arrow, and that's your X, that's your Y, that's your Z. You now create a new double bond between Y and Z, a single bond between X and Y, and then the positive charge migrates to X, from Z to X. Does that make sense? It follows the same scheme like the one in blue, that general arrow there. Same scheme. So that's how you always draw your resonance structure for the allyl system. And no matter how big, I will explain again this, no matter how huge the molecule is, what is important is your ability to see that allyl system in there. Once you're able to see the allyl system, then do what you know how to do. Push the arrows the same way we are doing. And when you push the arrow, observe the structure, the resulting structure, and ask yourself, can I do another resonance structure? If the answer is yes, you keep doing until you come back to the original structure. Does that make sense? Yes. Hey, you're in class. Yes. No. If you draw and come back to the original structure, you will not count that as a resonance structure because you already had it. Does that make sense? So that's why you know I have to stop. Because you know that if I draw it, I will come back to the original. So I have to stop. So you can do the same thing with the benzylic system. We can do the exact same thing with the benzylic system. That's my X. When you zoom this thing, you need to reduce the ink. That's my X, that's my Y, and that's my Z. Does that make sense? That's the most important, that ability to be able to extract that system. And so when you move the arrow, this is your X, that's your Y, that's your Z, you create a double bond there, and then you see the positive charge is now on X. Now what happens is this. When I observe this structure, I see in it another allelic system. When I observe my resonance structure, I see in it another allelic system. And let me reduce that ink size. Make it smaller. So when I observe here, I notice I have a new allelic system, my X, my Y, and my Z. Do you see that? I can see another allelic system in there. And then I do the same thing. I push the arrow exactly the same way, and I have this resulting molecule. And on that resulting molecule, I see another allelic system in there, XYZ. Do you see that? And you push the molecule, you have this. And when I have that, I see another allelic system, XYZ. And I push the arrows exactly the same way in order to have that. Then I notice that this guy is very similar to that guy over there. Then I stop. Does that make sense? So when I reach here, notice that this structure is not different from that structure. That's why you know you should stop. Does that make sense? How nice. It's good, right? Perfect. Let's try this example. Draw all the resonance structures for that molecule. Let's try that. Let's draw the resonance structures for that molecule. Make sure you're able to push your arrow, okay? Now, for as a hint, X equals Y minus Z with a negative charge. The way you push your arrow for this one, the electron goes there, and then this goes on top of X. So your resonance structure now will be X with a negative charge minus Y equals to Z with a positive charge. That's the general way. That's the general way in which you push your arrow when you have a negative charge on one of the atoms. Does that make sense? It's very similar to the way you push your arrow when you have a lone pair of electrons present. So that's the general way. With that general way, I expect you guys to be able to draw all the resonance structure for that particular molecule. Do we all have that? What I have on the board there? Do we all have that, right? Okay. So those are the different resonance structures you will have. So that's good for practice. That's just good for practice. You have more examples in your textbook. That's how you draw those resonance structures. So relative stability of yes. Yes, because these electrons here, you see these electrons, the one I'm drawing, they go over there and satisfy the plus. Does that? Yeah, they move. Yeah, which this oh, so well, yeah, when they go over there and satisfy the plus, that's why we have a minus on that oxygen. So that minus comes back. The oxygen gets back its original. Yeah, because this other minus here, that's what creates a bond here. Good question. Oh. Good question. Huh? Yes, there should be no positive charge on that oxygen. Yes, there should be no positive charge on the oxygen. Probably I'm infected. It should be without that positive. It should be without that positive. Okay, my bad. See, sometimes mistakes are possible. Relative stability of carbocations, okay? Now, based on what we've done already, we will now understand why the benzyl carbocation is the most stable, followed by the allyl carbocation, and then the tertiary, secondary, primary, and so on and so forth, okay? Now we understand it better because of all those possibilities of drawing those resonance structures. And again, you might have a possibility of having a tertiary allylic carbocation. So it is allylic and it's tertiary because the positive charge is on the tertiary carbon. So tertiary allylic will be more stable than a secondary allylic. That will be more stable than a primary allylic. Same thing with the benzylic. A tertiary benzylic will most likely be the most stable, followed by the secondary and then the primary. Does that make sense? Yeah. Okay, we're changing gears. We're talking about something completely different now. Let's talk about something a little bit different from what we've been doing so far. So the first part of this class was mostly to see how delocalization can affect stability, different ways in which delocalization can affect stability. Now we're talking about something else, the molecular orbital diagram. That's what MO stands for. Okay, MO stands for molecular orbital. An orbital is a region in space where you can easily find an electron. Does that make sense? That's what an orbital is. It's a region in space where you can easily find an electron. And for an atom, if you look at an atom, we'll represent that as what we refer to as an atomic orbital. Okay? And then for a molecule, it will be referred to as a molecular orbital. And you note that molecules are formed when you combine several atoms together. If you bring several atoms together, then that gives you a molecule. If I say a molecule of water, it's simply because I brought in 2 atoms of hydrogen and 1 atom of oxygen. I combine them, that's what gives me a molecule of water. Does that make sense? So molecular orbitals also obey that rule. If you want to form molecular orbitals, you have to bring atomic orbitals together. Does that make sense? That's what you guys did in 201. You remember that? Linear combination of atomic orbitals. So you are combining atomic orbitals together in order to generate molecular orbital. Is that okay? Now, the number of molecular orbitals you generate is proportional to the number of atomic orbitals that come together. So if you combine two atomic orbitals, you will generate two molecular orbitals. Does that make sense? If you combine three atomic orbitals together, you will generate three molecular orbitals. If you combine four atomic orbitals, you will generate four molecular orbitals. That's why it's called a linear combination. It's not an additional combination. It's a linear combination. So 2 gives 2, 4 gives 4, 3 gives 3. Does that make sense up to this point? Okay. Now, atomic orbitals, you know them. You know all those different atomic orbitals. The s orbital, the p orbital, those are all atomic orbitals. The d orbital, the f orbital, those are all atomic orbitals. sp2 is an atomic orbital, all those kind of stuff. Does that make sense? Those are atomic orbitals. Those atomic orbitals. So when you combine those atomic orbitals, you now form what we call a molecular orbital. So let's look at a molecule of 18. 18 has a double bond like that. Okay, carbon-carbon double bond. And each of these carbon, they have a p orbital. Does that make sense? Each of those carbon have a p orbital. So let's call this one p1 and call this one p2. So this is carbon 1, that's carbon 2. So the p orbital of carbon 1 is there, and then the p orbital of carbon 2 is there. And so those two orbitals now can interact with each other. They can interact with each other, they can combine. And so if they do that, they will generate a molecular orbital. Does that make sense? And so how many p orbitals do we have in here? 2. How many molecular orbitals are we expecting to form? 2. That's why we have those 2. Those are 2 molecular orbitals. Does that make sense? Those are the 2 molecular orbitals. So and you can see that this is most likely the p orbital from one of the carbon, and this guy here is most likely the p orbital from the other carbon. Does that make sense? So you're able to generate 2 molecular orbitals. Now, in this case, those 2 molecular orbitals obeys again the same rule as atomic orbital in terms of electronic configuration, filling in electron, all those principles you learn in Gen Chem, the Pauli exclusion principle, Hund's rule, in filling up electron. That electrons will usually go down to the orbitals of lower energy before they move to orbitals of higher energy. All those rules appear. All those rules happens in here. That makes sense? Now, how many pi electrons are present in this system, in the 18 system? How many pi electron? No, pi electron. There are 2. Because a pi bond is made up of 2 electrons. There's only 1 pi bond in 18. Does that make sense? 18 only has 1 pi bond. And so we have only 2 electrons. And so in this molecule, there are only 2 electrons to distribute in this electronic configuration. And those 2 electrons will go into the orbital of lower energy. That's why you have the 2 electrons standing there. So they get into the orbital of lower energy. Does that make sense? Now, the difference, the line separating those 2 orbitals, is called a boundary. There is a boundary that separates the 2 orbitals. Usually the orbitals above that boundary without electron, because they are deprived of electrons. The orbitals above the boundary without electron, we refer to them as the anti-bonding orbitals. So those are the anti-bonding orbitals. And the orbitals below the boundary that are filled with electrons are usually referred to as the bonding orbital. Does that make sense? We refer to them as the bonding orbital. Anti-bonding and bonding orbital. Those are the things I want you guys to be able to determine when you have this kind of molecular orbital diagram. Okay. Now, the next thing, what do you observe between the bonding and anti-bonding orbital? Observation. Let's start with observation. First thing we notice is that if I divide to split if I decide to split those orbitals into two, you will notice that this half is exactly the same as that half. It's that kind of mirror image. They look exactly the same, right? We describe to it as being symmetrical. Does that make sense? We refer to that as being symmetrical. What about this one? If I split that into two, you'll notice that this is exact opposite of the other one. Does that make sense? And because that's exact opposite, we refer to that as being anti-symmetrical. We'll say that orbital is anti-symmetrical. And so the way it moves, if you had a third orbital, that third orbital will most likely be symmetrical. So it goes symmetrical, anti-symmetrical, anti, until forever. That's one thing I want you guys to take note. Another term that we want to use here is what we refer to as the node. The node is that specific point where there is a change in symmetry. That's what we refer to as the node. That specific point where there is a change in symmetry is a node. And that node, the probability of finding an electron is 0 at the level of the node. So, the first orbital down here has 0 nodes. That's basically what we shall say. 0 node, meaning that there is no change of symmetry. 0 node. And then this other orbital up there we say has 1 node. Does that make sense? So this orbital over there we have 1 node. Does that make sense, guys? That's the way I want you guys to see this molecular orbital diagram. And we'll get to it and see how useful that is. Let's just try to make sure we are good with this nomenclature. Are we good? So we talked about the bonding and the anti-bonding orbital. We looked at the orbital symmetry. Orbitals that are symmetrical and orbitals that are anti-symmetrical. We looked at the number of nodes, a 0 node orbital and a 1 node orbital. We talked about the boundary. Orbitals above the boundary without electrons are anti-orbitals, and orbitals below the boundary filled with electrons are bonding orbitals. That's for a system with 2p atomic orbitals. Now, if we go to another system, 1,3-butadiene. If we look at the 1,3-butadiene, let's draw the structure. Butadiene, but it means 4 carbon. 1, 2, 3, and 4. Diene means we have a double bond, and those double bonds will be on carbon number 1 and carbon number 3. That's why it's called 1,3-butadiene. So on carbon number 1 I have a double bond, and on carbon number 3 I have a double bond. Does that make sense? All these atoms are sp2 hybridized. It means I have p orbitals over there. Now, how many pi electrons are involved in this system? There are 4 pi electrons. Does that make sense? There are 4 pi electrons because I have 2 double bonds. And each double bond will only have 2 pi electrons. So I have a total of 4 pi electrons. Now, how many molecular orbitals do I expect to have in this system? Does that make sense for everyone? We expect to have 4 molecular orbitals because we have 4 atomic orbitals. Okay? And these are the 4 molecular orbitals shown here. Those 4 molecular orbitals will be labeled as phi 1, phi 2, phi 3, and phi 4. Those are the 4 molecular orbitals. Does that make sense? Now we need to fill those orbitals with their electrons. We need to fill them with electrons. And so if you fill them with electrons, we have 4 electrons. The first orbital gets 2, then the next orbital, the other 2. Does that make sense? Those are the 4 pi electrons. Then we have that our famous boundary. That line that separates orbitals with electrons from orbitals without electrons. Okay, that's our boundary. Separates orbital with electrons from the ones without electrons. And all the orbitals above the boundary are anti-bonding. Those orbitals are anti-bonding. And the orbitals below the boundary are the bonding orbitals. Does that make sense? Below the boundary with electrons are bonding. Above the boundary without electrons are anti-bonding orbitals. Now let's talk about the symmetry. Let's look at the symmetry. Phi 1, the first orbital, is that orbital symmetrical or anti-symmetrical? The orbital is symmetrical. Does that make sense? That orbital is symmetrical. What about orbital number 2? Symmetrical or anti-symmetrical? It's anti-symmetrical. Because if I draw a line of symmetry here, I will notice that these orbitals are exact opposite of that one. Do you see that? So that's the anti-symmetry. So that orbital is anti-symmetrical. Now, from there, things move. Symmetrical, anti, okay? So this will be symmetrical, and this other one, phi 4, will definitely be anti-symmetrical. Now, another way of looking at the symmetry is that you only pay attention at the first and the last orbital. That's another way to look at symmetry. You only focus on the first and the last orbital. Look at phi 3. When I look at my first orbital and I look at the last orbital, I see that they are the same. Does that make sense? Once the first and the last orbital look exactly the same, we refer to them as being symmetrical. Is that okay? And if you look at number 4, to compare the first and the last orbital, you will notice that they are opposite to each other. That's why we refer to that as anti-symmetrical. Yes?
Okay, so why are they opposite?
Why are they opposite? Yeah, if you have to draw that, that's why I say the first orbitals are always symmetrical. Second orbital anti. Third orbital symmetrical. Fourth orbital anti. And so it keeps moving in that pattern. Does that make sense? Now, another thing you need to take into consideration are the nodes. The first orbital will always have a zero node. Remember, the node is that point where there is a change in symmetry. That's the node, where you have that change in symmetry. So the first orbital will have a zero node. In this case, our second orbital will have one node. Because you start with zero node, then you move to 1, 2, 3, 4, 5. And the way you draw your node, you always try to draw the node in such a way that you split your orbitals evenly. So for the first node, to draw a one node, there's only one way I can split my orbital to make things even, is to split that in between them. Okay? Now, the second orbital or the third orbital will be an orbital with two nodes. That will be my first node, and you notice that there's a change in symmetry there. Then, I cannot draw the second node here because if I draw a second node here, I will have to switch the symmetry. Wherever a node goes, there's a switch in symmetry. If you don't have a node, then there will be no switch in symmetry. And so the second node will be here. That's why I now have a switch in symmetry between those two orbitals. This orbital is opposite to that one. So orbitals on both sides of the nodes will always have an opposite symmetry. Does that make sense? And you can do the same thing with the fourth orbital. So the fourth orbital will have three nodes. Yes?
Do you guys know how to draw it?
Yes.
Okay, so I don't understand how. I don't understand when do you put it together as something or when you put it together. How do you do it? Let me look for a blank paper here. How do I open a blank document?
Okay, I have a blank document. Let's do butadiene, the one we just did before, and draw it together. Okay, so that's my butadiene over there, and each of them will have a p orbital. I know they all have a p orbital, so there are 4 p orbitals. And because there are 4 p orbitals, I know that I will have 4 molecular orbitals. Does that make sense? So I draw my 4 molecular orbitals. Hey, if they don't look good, just bear with me, okay? I'm not very good at drawing. So those are my 4 molecular orbitals, right? Those are the 4 molecular orbitals. Now the next thing I know is that I have a total of 4 pi electrons. I have a total of 4 pi electrons. And so those 4 pi electrons, I will now have to fill them into this orbital. The one with lower energy get the first 2 electrons, followed by the next one that's lower in energy. And I have used all my pi electrons. Does that make sense? So because I've used all the pi electrons, I can now have my boundary that will separate orbitals with electrons from orbitals without electrons. Does that make sense? The orbitals with electrons, we'll call them bonding, and the orbitals without electron, we'll call them anti-bonding. We'll refer to those as anti-bonding. Are we good up to this point? Okay. Now, what I know, like I told you, is that the first orbital will always be symmetrical. The second orbital will be anti-symmetrical. The third will be symmetrical. And the fourth will be anti-symmetrical. That's what you know. Okay. In terms of the node, the first orbital will always have a 0 node. The second orbital will have 1 node. This will have 2 nodes, and that will have 3 nodes. Remember, a node is a point where there's a change in symmetry. Since the first one will have a 0 node, it means that they will all have the same symmetry. It means there will be no change in symmetry. So all of them will be that way. That's the way I can draw them without a node. Does that make sense? 0 node. Now the second one has 1 node. The second one will have 1 node. Let's do a different example. Where can we draw? How do I know where to draw my 1 node? That's the point. If I decide to draw the node here, if I decide to put the node here, what I know is that this guy will have an opposite symmetry to that guy, because that's why I decided to draw my node. And I know I can only have 1 node. And if I can only have 1 node, the remaining 2 orbitals can only be painted on the bottom one. Does that make sense? But then remember, we said that orbital needs to be anti-symmetric. Is that orbital anti-symmetric? Yes, it is. From the first one and the last one, they are anti-symmetric. But the problem is that you want the node to be equally, to divide the orbitals as equal as possible. You want to be fair as possible. Does that make sense? You want to share that as equal as possible. So if you draw the 1 node over there, it won't be good, because that's not the best way. That's not equal. And so the only way I can make it equal is by putting my node over there. And if I put the node over there, then this guy will have that painting. So that's where my 1 node will be. The guy with 2 nodes, I need to draw the guy with 2 nodes. The guy with 2 nodes over here, I think by putting a node here and by putting a node here, that will be the best possible way of doing it. So that if this is painted up, this will be painted down. There is no note, so this is also painted down. And because I see a note, I now go up. Does that make sense? I started up, then I see a note, then I have to go down. I don't see any note, I maintain it down. When I see a note, I change my direction. Does that make sense? And you can do the same thing with the third one. The third one will need to have 3 notes. 1, 2, 3. Those are the 3 notes. I start from the top. Oh, I see a note, I go down. I see a note, I go up. I see a note, I go down. Does that make sense? That's a molecular orbital diagram. If you cannot draw this, at least know how to label it. Does that make sense? If you cannot draw, know how to label it. Know how to label where the notes are. If it is drawn for you, know where to put the note. Know if the orbital is symmetrical. Know which orbitals are bonding. Know which orbitals are anti-bonding. Does that make sense? Now, the last thing I have to mention on this molecular orbital diagram, okay, these 2 orbitals here, the one directly above the boundary and the one directly below the boundary, are very important orbitals. That's why El Paso is an important city. That's why border cities are very important, right? That's why they were told to build a wall. Border cities are important because people can move from one city and cross the border and go to the other one very easily. Does that make sense? It's the same story. That's why I say life is chemistry. Life is chemistry. The guys that live in the border can easily interchange. They can easily move. And so those guys will call them frontier orbitals. Those are the frontier orbitals. They are very important orbitals. The frontier orbitals. Very important. And the one that is above the boundary, we'll call it the LUMO. That LUMO stands for lowest unoccupied molecular orbital. We refer to that as the LUMO, meaning the lowest unoccupied molecular orbital. And the guy that is down, what name do you think we should give him to this guy? Who said it? What does that mean? Yes, so we'll call that the highest occupied molecular orbital. Those 2 orbitals are referred to as frontier molecular orbitals. Okay? Because those are the guys that are involved with the reaction. And that's why sometimes if you read articles, people will always say the HOMO-LUMO interaction. Meaning that, that's where things happen. That's where life happens. And that's why it's important for us. So like I said, if you cannot draw it, at least know how to label it. Know how to label it. So the next couple of slides basically explain what we've done already. So this slide explains to you what a symmetrical orbital is and what an anti-symmetrical orbital is. So this orbital here is symmetrical. This other orbital here is anti-symmetrical. Like I said, don't only focus on the first and the last orbital. First and last, the symmetry is the same, so symmetrical. First and last, symmetry is the same. Symmetrical. Now, on this other one, first and last, symmetries are not the same, anti-symmetrical. The first and the last, the symmetries are not the same, so anti-symmetrical. Does that make sense? A couple of slides here will only be explaining what we've seen before. So, this will be the molecular orbital diagram of an isolated system. That's how the molecular orbital for an isolated system will be. And this is how the molecular orbital for a conjugated system will be. You notice that for an isolated system, you have an sp3 carbon that is separating those orbitals. Remember, that's why we talked about isolated system. At least one sp3 carbon that separates the double bond becomes an isolated system. And this will be the molecular orbital of a conjugated system. Yes, Maria. Yeah, isolated system will not be able to show resonance. So are we good up to this point? But most of our focus will be on the conjugated system. Okay. Resonance can affect the pKa. Remember what pKa is? It's a measure of the acidity and basicity of a molecule. So resonance can affect the value of the pKa of a molecule. So a carboxylic acid is stronger. An acid is a stronger acid than an alcohol because of the inductive withdrawal effect of the electron of delocalization. Take note. Let's think back from the beginning. We have HCl versus HI. In Gen Chem, which of these is a stronger acid? HCl or HI? I'll send it back to Gen Chem. HI is a stronger acid. Hydrogen iodide is a stronger acid than HCl. Does that make sense? Hydrogen iodide is a stronger acid than HCl. It means that hydrogen iodide will have a smaller pKa than HCl. How do I know that? It's because I look at the conjugate base. This will dissociate to give you that. And this one will dissociate to give you this. This is why I focus on the Cl minus and the I minus. Between Cl minus and I minus, which one is more stable? I minus is more stable. That's why HI is a stronger acid. HI is a stronger acid so that it can react faster to generate I minus. I minus is more stable. So if you have a stable conjugate base, then your acid is a strong one. Does that make sense? If you have a stable conjugate base, your acid is a strong one. So you can start imagining how resonance can affect acidity. The more resonance structure you form, what happens? The more stable you are. And so if you are stable, then your acid will probably be strong. I hope it makes sense. Let's think about this. Alcohols and carboxylic acids. Alcohols and carboxylic acids. On the board here we have acetic acid and we have ethanol. This is acetic acid. So if acetic acid decides to react, this is the hydrogen there. By losing that hydrogen, it will produce H plus CH3 carbon, double bond oxygen, single bond oxygen with a negative charge. Do you see that? If the alcohol decides to react, it will give H plus CH3 CH2 O minus. Can you guys see that? I will zoom it there. Let's focus on the conjugate bases. This is a conjugate base of acetic acid. This is a conjugate base of ethanol. Between those two conjugate bases, which one can undergo resonance? This is conjugate base A and this is conjugate base B. Between conjugate base A and conjugate base B, which one can undergo resonance? A can undergo resonance. It means that conjugate base A is more stable than conjugate base B. Does that make sense? And because the conjugate base is more stable, then your acid will be stronger. So that's why acetic acid is a stronger acid than ethanol. I don't know if it makes sense. Okay? And I think the next slide will only be explaining what I have said already. So this slide is basically explaining exactly what I said. So those are simply the two different resonance structures these are the resonance structures for acetic acid. And so it's because of this resonance structure that the other guy now becomes a stronger acid. Does that make sense? And ethanol cannot have that. Phenol versus cyclohexanol. Which one is a stronger acid? How can we rationalize the fact that phenol is a stronger acid? Because remember, the lower the pKa, the stronger the acidity. How can we rationalize the fact that phenol is a stronger acid than hexanol? Resonance of the conjugate base. Does that make sense? Of the conjugate base. And so what I do, I need to draw the conjugate base for this guy. The conjugate base for this guy will be that one. And we've drawn the resonance structure for that molecule in this class already. Okay? And the conjugate base for this one will be that one. This can undergo resonance. This cannot undergo resonance. And because this can undergo resonance, it gives you a stable conjugate base, and so the acid is a stronger one. Does that make sense? And we've done the resonance structure for that in this class already. And this slide is basically saying what I'm saying. No delocalization, so you are not good. This one is saying exactly what I'm saying. This is the one we did in class today. That's the one we did together. Okay? And you see we have a lot of delocalization over there. And because we have that delocalization, then it makes it a greater acid. Same story with this other one. You guys, you can do the same thing. You can explain it the same way, right? Why is this one having a strong, why is this one a stronger acid and this one a weaker acid? Same thing, you can do resonance here, but you cannot do resonance over there. Does that make sense? Yeah, life is the same. We all do the same thing in chemistry. No delocalization. And the other one, you can see the other one with the delocalization. As I'm saying that you can see, I'm not asking you to see, I'm asking you to do. So go and draw those resonance structures on your own. And practice how to draw them. Does that make sense? Yes, practice. To summarize, I have 30 seconds. So that's basically it with my summary in terms of pKa. The smaller the pKa, the stronger the acidity. Okay, the smaller the pKa, the stronger the acidity. Usually an oxygen with a positive charge and a nitrogen with a positive charge are always more acidic than any other one. Okay, because they really want to lose that hydrogen. They really want to lose the hydrogen. So next class we'll talk about electronic effects. Yes. Say that again. Yes, it will be extended. Just go ahead, keep doing it. Keep doing it. Keep doing it.
I have an appointment at 3.
Uh-huh.